Hello everyone, my name is Sunwoo Kim from KAIST AI. Today, I would like to introduce my research, How Transitive or Real-World Group Interactions. This work is a collaborative work with Fanchen, Minyoung, Choe, Jaemin, and Kijung, Shin. Let me begin my presentation. I would like to first give an overview of our work. Group interactions are everywhere around us. Examples are group chatting on social media, co-authorship of researchers, interactions of proteins, and emails. These group interactions can be represented as a hypergraph. Here, the researchers' co-authorship shown in the left-hand side figure can be represented in the right-hand side hypergraph, where nodes indicate the researchers and hyperedges indicate the group of researchers who co-authored publications. Moving on to another topic, transitivity, the probability of two neighbors of a node being also adjacent is widely used in various domains, including neuroscience, link prediction, and so on. Despite the prevalence of group interactions and the importance of transitivity, there have been no systematic attempts to measure the transitivity of group interactions. Then, how can we measure it? Due to the complicated nature of a hypergraph, where multiple hyperedges overlap, this task is not trivial. Importantly, existing hypergraph transitivity measures focus on pairwise interactions rather than group interactions. They usually concentrate on whether two nodes are neighbors or not. And thus, as shown in the middle figure, the two cases are equivalent in terms of transitivity when we use such existing measures. This implies that it is inappropriate to use such measures to capture the transitivity of group interactions. We now introduce our proposed transitivity measure. We first describe several basic terminologies. Hyperwedge is a set of two joint hyperedges where one hyperedge is not a subset of another. Here, left wing and right wing are the sets of nodes where the intersection of two hyperedges is excluded from two hyperedges of a hyperwedge. At last, a body group is an intersection of two hyperedges. In this setting, our primary goal is to assess the group interactions between the left wing and the right wing. Moreover, we define transitivity measures on two different levels. One is a hyperwedge level measure that measures the transitivity of a given hyperwedge. The other is a hypergraph level measure that measures the transitivity of a given hypergraph. Note that we aim to design a principled measure. Then, how can we say a specific measure is principled? To assess it, we provide 7 axioms to formally describe such desirable properties of a principled transitivity measure. That is, if a measure satisfies all the axioms, then we can conclude that the corresponding measure is principled. Axiom 1 to 5 describe the conditions of a hyperwedge level transitivity measure. Specifically, Axiom 1 and Axiom 4 describe when the value of a hyperwedge transitivity measure is minimized or maximized respectively. In addition, Axiom 2 and Axiom 3 formalize how the value of a hyperwedge transitivity varies under certain conditions. At last, Axiom 5 describes the bound of a hyperwedge transitivity measure. Let me describe Axiom 1 and Axiom 2, case 3 in detail. First, Axiom 1 describes when a measure achieves its minimum value. It should be minimized when there is no hyperedge that intersects with both wings. An example is shown in the below figure. Second, Axiom 2, case 3 describes how the value of a measure varies when a new hyperedge arrives. Specifically, when a new hyperedge includes a new pair interactions between two wings, then the transitivity value should increase. An example is shown in the below figure. At last, Axiom 6 and 7 describe the conditions of a hypergraph level transitivity measure. Specifically, Axiom 6 describes how should the value of the transitivity measure be when the graph is an ordinary graph. Moreover, Axiom 7 describes the bound of a hypergraph transitivity measure. We introduce our proposed transitivity measure, hypertrans. First, hyperwedge level hypertrans is an average of scores of pair interactions between the nodes in the left wing and those in the right wing. For example, assume a hyperwedge consists of E1 and E2. There are 3 overlapping hyperedges, E3, E4, and E5. Here, there are 9 pair interactions between two wings, and they are shown on the bottom side of the slide. We now describe how we compute scores of each pair interaction. There are 3 steps in score computation as shown in the slide. First, we find hyperedges that contain the pair of our interest. For example, for a pair of node 1 and node 4, there are 2 overlapping hyperedges, E3 and E4. Next, we compute scores of the bound hyperedges. Here, score of a hyperedge E in a hyperedge W is the quantified contribution of E to the interaction between the left wing and the right wing. One example of such score is shown below, which is a variant of a Jacquard similarity. We use this function as a score function in this presentation. And thus, the score of hyperedge E3 and E4 become 2 upon 9 and 4 upon 9 respectively. At last, we find the maximum score among them and regard it as the score of the target pair. In this case, the score of E4 is the maximum score, and the score of a pair node 1 and node 4 becomes 4 upon 9. We do the same process on a pair of node 1 and node 5, and here, since there is only one overlapping hyperedge, which is E4, the score of this pair becomes 4 upon 9 as well. On the other hand, note that there is no hyperedge that contains a pair of node 1 and node 6. In this case, the score of the corresponding pair becomes 0. We perform this process on the entire pairs. At last, we compute an average of all scores, and the resulting average value, which is 17 upon 81, is a hyperwedge transitivity value computed by a hyperwedge level hypertrans. Extending this, hypergraph level hypertrans is an average of all hyperwedge level hypertrans of a given hypergraph. In this example, there are 5 hyperwedges. We compute an average of their transitivities, which is 11 upon 50, and this is a hypergraph transitivity value computed by a hypergraph level hypertrans. There are formal expression of the proposed measure hypertrans. At a hyperwedge level, each term in an expression performs the mentioned algorithm. Let me describe this in more detail. The navy term rotates each pair interaction. The blue term checks which hyperedge includes the corresponding pair. The red term computes the score of such hyperedges. The purple term finds the maximum score, and the green term computes the average. At a hypergraph level, which is relatively simple, each term performs the following task. The green term rotates the entire hyperwedge. The blue term computes the corresponding hyperwedge's transitivity, and the red term computes the average of such transitivities. We now introduce our observations. We have analyzed the transitivity patterns in real-world hypergraphs at 4 different levels: hypergraph, hyperwedge, node, and hyperedge. In order to demonstrate that the observed patterns are not random behaviors, we have generated random counterparts of each real-world hypergraph by using HyperCL, which can preserve the expected node degree distribution. If certain patterns in real-world hypergraphs are not observed in randomized ones, we can conclude that such patterns are unique to the real-world hypergraphs. The first observation is about hypergraph level. Real-world hypergraphs are more transitive than randomized hypergraphs. As shown in the table, real-world hypergraphs show a higher hypergraph transitivity value than their random counterparts, and differences among them are all statistically significant under the significance level of 0.05. The second observation is about hyperwedge level. There exist positive correlations between body group sizes and hyperwedge transitivities in real-world hypergraphs, while such a pattern is not observed in randomized hypergraphs. As shown in the table, real-world hypergraphs consistently show the positive Spearman rank correlation between hyperwedge transitivities and body group sizes. This is intuitive, since a large body group implies 2 interactions share many nodes, and such interactions are likely to form another group interactions as well. The third observation is about node level. In real-world hypergraphs, the transitivity of a node is negatively correlated to its degree. As you can see from the left-hand side figure, down to the right plots of real-world hypergraphs demonstrate such negative correlations. This result is also intuitive. When we think of an extroverted person who has been involved in many group interactions, his friends in different groups are less likely to know each other, although both of them know the extroverted person. On the other hand, friends of an introverted person are also likely to know each other, since the introverted person usually involved in a few group interactions. At last, at the hyper-edge level, real-world hypergraphs have wider ranges of hyper-edge transitivity than their random counterparts. This result can be shown in the left-hand side table. That is, the hyper-edge transitivity of real-world hypergraphs can achieve both the maximum and the minimum value of a measure, while that of random counterparts cannot achieve the maximum value in general. Now we describe our proposed generator. Note that realistic synthetic hypergraph generator is useful in finding causes of patterns, simulation, upscaling, and anonymization. We propose a transitivity-preserving hypergraph generator, Thera. Thera is based on a community structure of nodes. Specifically, Thera randomly assigns nodes to communities and creates hyperedges within each community. We first introduce our preliminary approach, Knife Thera. Knife Thera only creates intra-community hyperedges, assigning each node to a community and creates only intra-community hyperedges. As shown in the below figure, we can control the transitivity of generated hypergraphs by adjusting the size of each community. However, Knife Thera fails in generating realistic hypergraphs. This is because generated hypergraphs have near uniform node degree distribution and they are disconnected. Thera, our proposed hypergraph generator, mitigates such issues by generating another type of hyperedge. There are two types of hyperedges. The first, intra-community hyperedge, is identical to the generation method of Knife Thera. The second hyperedge, which differs from Knife Thera, is a hierarchical hyperedge. To generate hierarchical hyperedge, Thera assigns each node a level in the tree and creates hyperedges by sampling nodes proportional to the level of each node. Specifically, nodes at the upper side of the tree are more likely to be sampled, and the nodes are sampled regardless of the communities they are involved. And thus, near uniform degree distribution and disconnected hypergraph issues can be mitigated. Let me introduce more details of generation steps. First, Thera introduces a single node at the top of the tree. Then, it introduces predetermined number of nodes in the next level of the tree. After, Thera stochastically determines the type and the size of the current hyperedge. Note that the type becomes intra-community proportional to P or hierarchical proportional to 1 minus P, and it samples the size from the real hyperedge size distribution. If a hyperedge is decided to be an intra-community hyperedge, it creates a hyperedge within the community. If a hyperedge is decided to be a hierarchical hyperedge, it samples nodes from the introduced node sets proportional to the level of each node and fills a hyperedge with sampled nodes. Note that nodes at the upper side of the tree are more likely to be sampled. Now, we introduce more nodes in the next level of the tree. Note that the upper sides of the tree contain less nodes than the lower sides. Then, we again decide hyperedge type and size as mentioned earlier. Here, if you are creating intra-community hyperedge with a node 8, we sample nodes from a community of node 8, which are green-colored nodes. Similarly, if we are creating intra-community hyperedge with a node 14, we sample nodes from a community of node 14, which are cyan-colored nodes. If a hyperedge is decided to be a hierarchical hyperedge, Methods are identical to the aforementioned hierarchical process. Note that more nodes have been appeared in the tree, and the sample space is larger than the previous case. We have covered how Thera works. Now, we verify how well Thera reproduces the transitivity patterns of real-world hypergraphs. Specifically, we investigate whether Thera reproduces observation 1 to observation 4 well. First, as shown in the table, Thera preserved the hypergraph transitivity and the hyperwedge transitivity distribution most well among the 6 generators. Second, Thera has well preserved observation 2, the positive correlation between hyperwedge transitivities and body group sizes, and observation 3, the negative correlation between node transitivities and node degree. At last, Thera also preserves the range of hyperwedge transitivity well, wide as that of the real-world hypergraphs. Regarding the complexity, among the 3 incremental generators, Thera has the least time and memory complexity. Especially, Thera can generate a hypergraph of nearly 31 million hyperedges within a minute. Furthermore, Thera achieves the fastest generation time and the least memory consumption among the 5 hypergraph generators. Now I'd like to wrap up the presentation. In this work, we present, first, criteria that a principal measure should have. Second, a principal measure hypertrends. Third, analysis of the real-world hypergraphs. Fourth, pattern-preserving scalable hypergraph generator, Thera. Refer to the following links for the paper and GitHub. Thank you for listening.